Alright guys, so today we are going to cover condensation and hydrolysis reactions. So a condensation reaction is where two or more molecules combine to form a larger molecule with the simultaneous loss of water. So this is a type of double replacement reaction that looks like this. So we're essentially going to react two smaller molecules together to form a bigger molecule, and we're going to create water in the process. So what larger molecule do you think we would be creating in a reaction called esterification? That's right, we are going to form an ester. So what two small molecules do we need as reactants? So think about what residues make up an ester. So an ester is made up of carboxylic acid and alcohol residues. Therefore, we need a carboxylic acid and an alcohol to perform this reaction. And this is a very slow reaction, so we are going to catalyze it using a trace amount of acid. And you'll see this written a lot of different ways. The most common way you'll see an acid as a catalyst is H+. That's because when an acid dissociates, it's going to dissociate into its conjugate base and H+. You'll also see it written sometimes as a dehydrating agent. A dehydrating agent is a substance that dries or removes water. So in the eyes of a chemist, a dehydrating agent is something that drives a condensation reaction. Sometimes you'll see a specific dehydrating agent or acid listed as the catalyst. The most common is sulfuric acid, but just about any inorganic acid will work. Okay, so let's try an example. So go ahead and pause this video, see if you can name the reactants, predict our products, and name the products. Okay, so we'll start by naming our carboxylic acid reactant. So our carboxylic acid reactant has 3 carbons. So a 3-carbon carboxylic acid is propanoic acid. Okay, now let's name our alcohol. So we have a 2-carbon alcohol, and a 2-carbon alcohol is ethanol. Okay, so we're going to react these together. Remember, this is a double replacement reaction, and our products are always an ester and water. So one thing that helps when doing reactions like this is to circle where the water is coming from. So where on our reactants is the water molecule coming from? So the water is going to be formed by the hydrogen attached to the oxygen on our alcohol and the OH from our carboxylic acid. And then to form our ester product, we're just going to connect everything else together. So one thing I like to do when doing ester reactions is start with what I know. So every ester is going to have a carbonyl attached to an oxygen. So I'm going to always start by drawing those 3 atoms. And now I'm going to fill in my alcohol residue and my carboxylic acid residue. So we started with a 2-carbon alcohol. So our alcohol residue should have 2 carbons. And the carboxylic acid that we started with had 3 carbons. So our carboxylic acid residue, part of our ester, also has to have 3 carbons. And remember, the carbonyl carbon counts as one of your carbons for your carboxylic acid residue. Okay, so let's go ahead and name our products. So we know H2O is water, that's the easy one. And our ester, we're going to start by listing the alkyl group that makes up our alcohol residue. Then we're going to take our carboxylic acid residue, and we're going to drop the oic acid and replace it with O8. So that gives us a final IUPAC name of ethyl propanoate for our ester. Okay, so notice that this reaction uses a double arrow. So do you remember from your last class what that double arrow means? So that means that this is a reversible reaction. So we can hydrolyze the ester to yield a carboxylic acid and an alcohol. So if we're hydrolyzing something, that means we are performing a hydrolysis reaction. And a hydrolysis reaction is the opposite of a condensation reaction. This is where we're going to split a larger molecule into smaller components through the addition of water. So this is going to be another double replacement reaction, but this time water is going to act as a reactant. Okay, so let's try an example. So go ahead and pause this video and see if you can write a reaction for the hydrolysis of butyl ethanoate. Okay, let's see what you came up with. So the first thing we got to do is draw butyl ethanoate. So like always, when I'm drawing an ester, I'm going to start with the 3 atoms I know every ester has to have. The carbonyl attached to an oxygen. Okay, so let's fill in our alcohol residue first. So our alcohol residue should have a butyl group, so that's 4 carbons. So ethanoate tells us that our carboxylic acid residue should have 2 carbons. And since this is a hydrolysis reaction, we have to react this with water. And this is a reversible reaction that requires an acid catalyst. Okay, so this is a double replacement reaction. We're going to split our ester into a carboxylic acid and an alcohol. So one thing that helps me with reactions like this is to go ahead and indicate where on our reactant we're going to split it up. So I'm going to draw a little squiggly line between our carboxylic acid residue and our alcohol residue. Okay, so let's draw our products. We'll start with our carboxylic acid. So our carboxylic acid should have 2 carbons, and our alcohol should have 4 carbons. And we'll go ahead and name our products. So a 2-carbon carboxylic acid is ethanoic acid, and a 4-carbon alcohol, where the OH is attached at one of the terminal carbons, would be 1-butanol. Okay, so another common reaction that we can do with esters, and this is one that you're going to do in a lab later this semester, is the saponification reaction. So a saponification reaction is where we hydrolyze an ester using a strong base and heat. And I want you to view this reaction as a combination of 2 separate reactions. First, we're going to perform an ester hydrolysis. Second, we're going to perform a weak acid strong base neutralization reaction like you learned about in the previous video. So let's give this a shot. So I want you to pause this video and try to draw and name the products when pentyl methanoate is saponified. Okay, let's see what you came up with. So the first thing we have to do is draw pentyl methanoate. So like always, I'm going to start with my carbonyl attached to my oxygen. So pentyl tells us that our alcohol residue should have 5 carbons, and our carboxylic acid residue should only have 1 carbon, which we already have, so our molecule should be good to go. Okay, so we'll perform step 1, the hydrolysis part of the reaction first. And just like before, I'm going to draw a little squiggly line between my carboxylic acid and my alcohol residues. Okay, so we'll draw our carboxylic acid product, which should only have a single carbon, and our alcohol, which should have 5 carbons. Okay, and now our second part of the reaction. We're going to perform an acid-base neutralization between our carboxylic acid and our strong base. And in this case, we'll use sodium hydroxide as our strong base. Okay, so our alcohol is not going to be involved in this reaction, so we can go ahead and draw it on the right side of this arrow. And we're going to have a double replacement take place between our carboxylic acid and our strong base. So remember, just like we talked about in the previous video, we're just going to swap the anions. So that means one of our products is going to be water, and our other product is going to be a salt. Okay, so if you haven't already, go ahead and pause this video and see if you can name our final organic products. Okay, so we have an alcohol with 5 carbons, and the hydroxy group is attached to one of the terminal carbons. So the name of that molecule would be 1-pentanol. So remember, we're going to name salts by listing our cation first, followed by our anion, giving us a final IUPAC name of sodium methanoate. And so lots of times you will see a simplified version of the saponification reaction written, where we can remove substances that appear on both sides of the reaction. So we both started with water and ended with water. So a lot of times you will see water omitted from saponification reactions. and the reaction will be simplified like this.